wrong.
What?
It's wrong.
And this is the electromagnetic from the magnet. You put it here. It shows that the gravity is a very weak force. When you apply the electromagnetic on this one, it's very weak.
Kalau kita ikat sesuatu kat situ, kita tak jatuh.
This is because of the ikatan.
Kalau ikat,
It's a mechanical force. Like this, right? So hold by the mechanical one. I can hold the gravity.
okay.
So the gravity is very weak.
It's very weak.
Okay? So this is the weak force. Electromagnetism, strong force, everything we can prove in experiment. Then gravity, we have what we call the graviton. It's not yet observed. Okay, this is a very clear one. This is from the Big Bang. And that is what we call the Planck error. And you can see this is the exponentially decay, the gravity. Go to the weaker force. And this is the Planck constant that we can calculate at 10 power negative 43. This is a small amount of energy per frequency in quantum mechanics. The weakness of gravity is difficult to maintain in quantum mechanics theory, much as it's difficult to balance the pressure on the tissue. It's very weak. When you couple with the quantum mechanical theory, you have a big problem to make it balance. Like you put the tension, then you want to stabilize the tension on the tip. So this is the same. What you want to find is the theory of everything. You want to unify this one. We call it grand unified force or theoretical unified force. In physics, when you reach when you have the size and you have the speed, and then you put the speed and you put the size. This is about the speed of sound. This is a super fighter jet, and then you have the highest speed is the speed of light. You have another scale, you have a micron one, and then you have the planet size. And you divide it by 4. The first one is classical mechanics. This is what we learn in school. It's about the micron size to the planet size and before the speed of light. And when you consider the same size, when you consider the speed of light, what we call the relativity mechanics. And when you consider lesser speed of light and the size of the 1 micron below to the nano size, this is what we call the quantum mechanics. When you combine this is what we call quantum field theory. This part, we work on the cosmology to study the string theory. Okay? So this is the size. The Planck length is about 10 power negative 30 meters. This is the size of the atom. This is the size of the multiverse. This is the size of the universe, 10 power 30 meters. One of the important about the understanding of the universe is the general relativity. It's published by Einstein in 1916, and with the help of the mathematician. Einstein will not have a good mathematics to explore the study of the cancer. So he had a very good friend, Michael Grossman. Until now, they order the Grossman as a Michael Grossman meeting. It's a 14 now. This year, July, at Rome. So what is the general relativity all about? This is the standard formula of general relativity. It's not, myself is not good in this one. Okay? But to show to you the general relativity comes from this Einstein field equation. It's all about the right hand side. It's all about the properties, geometrical properties of space, which is curvature, and the left hand side is the effect of the mass on the geometry. It's all about the tensor. For the first one, when Einstein published in 1916, he put the cosmological constant because to make sure this solution agree with the static universe. From the first study on the universe, during Einstein time, they believe the universe is static. There's no Big Bang. It's ready-made. So he put the cosmological constant. So now, in 2011, they calculated again. This cosmological constant is about 1.6 times 10 power negative 122. 0. So this part is 0. Okay, so this is what Einstein explained, that the gravity as the curvature of space-time. You have this as space-time. When I curve this one, or I curve like this is a gravity. This is what Einstein said, this is gravity. This is space, 3D, and you have time, and then you curve it, curve like this, or anything. This is what Einstein said, that this is how to explain the gravity. It's all about geometry. Okay, so you have a universe expansion. This is from the book, using a Poisson equation. They find out they have Hubble constant. And the final one, they have this one. This is how they explain the shape of the universe. Now they say that if you state that the left side is equal to 0, then this omega 1 is equal to 1. So the curvature of K is equal to 0. There is no curve. It means that the universe is flat. This is our universe right now. And then, by Einstein's field equation, they come up with the Schwarzschild radius. This is from classical mechanics. This is the mass of the planet. This is the speed of light. And this is a Newton gravitational constant. For Earth, if you calculate this one, you put the mass of the Earth, you find out the Earth is about 9 millimeters. If you put the size, it's about 3 kilometers. This is what we call the black hole. When you compress the Earth and become the size of the radius of the Earth is 9 millimeters, then you can create the black hole here on top. Everything is, with no object can escape from the gravitational attraction that we call the singularity. This is what they found out, the black hole, the idea of the black hole. This is about the expansion. This is about the three types of the universe from this equation. When you have is less than 1, it's a critical density. This is what we call the orphan universe, like this. This is all in mathematics. And then if the omega is greater than 1, the greater than critical density, we have the spherical shape. This is the opposite of the Big Bang. Then we have the Big Crunch. Big Bang, Big Crunch. Okay, so this is what we call closed universe. And up to now, all the scientists now believe in this flat universe. Where this is equal to 1, the universe is considered flat, infinitely size. This is what we believe, they believe, from their calculation, the universe now is a flat universe.